Right, let's start the evening session. I have my great pleasure to introduce Spencer Leslie from Boston College, who is going to speak on endoscopy for symmetric varieties.
Thank you very much. I want to thank Spencer as well for inviting me and putting this on. I really appreciate being here. This is actually, I guess, the first time I've been able to meet so many of you, because I guess by trade I do automorphic representation theory, but somehow we've been thinking about similar things for a long time. And so the goal of my talk today is somewhat modest. What I would like to do is sort of explain why I've been thinking about these things from the point of view of automorphic forms, and then propose a definition for endoscopic symmetric varieties in some generality, state a few results, and then kind of end with some examples and maybe some applications. So maybe I'll just start by recalling some of the things that thankfully Thomas talked about last talk. So I'll let K be any field, or okay, let me say K a field, and I guess I will also assume that the characteristic of K is it's never two. And let's assume that it's good. So as I'll try to copy most of Thomas's notation just for parsimony, but I'll let G be a reductive group over K. And I'll equip it with an algebraic involution, theta squared equal to 2 for I. And for simplicity, I'll set H equal to the fixed points of G, though, as Thomas indicated, you tend to want to work more generally within the normalizer subgroup, which will come up later in the talk. And so on the Lie algebra, we have this grading. So I'll use H just because if I try to switch my H's to K's, I'll get confused. Of the Lie algebra, and as in Thomas's talk, what one may be interested in is using this to define a relative analog of the Hitchin vibration. So we'll consider the quotient stack of H on P to the categorical quotient. Oh, I wanted to switch these. And so if one is, let's say K is the function field for some smooth projective curve over a finite field called K naught, then as has been seen in a couple talks, we can sort of form the mapping stacks into these two quotient stacks, and we get our relative Hitchin vibration. And so I'm going to fix a notation from here on out. I'll set X to be G mod H. So that will be my symmetric variety. So it's be MX, and that's AX. And so this is the relative Hitchin map that showed up in Thomas's talk.
So K naught is any finite field. It doesn't need to have any relation with your starting K.
Oh, sorry. I'm assuming in this case that K is. Yeah.
Okay.
Right. Okay, so in about 2018, I started thinking about this from the point of view of the relative trace formula, and in particular, I was motivated to try and prove maybe support type results generalizing Ngo's work in the classical, in the setting of the Hitchin vibration to this setting. And so some of what I was able to prove showed up in the previous talk. And so maybe I'll just briefly say that in this situation, so let's assume that this involution is quasi-split. So this notion has come up in the prior two talks. It just means that, for example, that means that the regular locus of P is a subset of the regular locus of G. So in this situation, I wrote down there exists a smooth. I also need a little bit more notation. So I'll let A and P be maximal abelian. Right, and so in this situation, the Chevalier isomorphism theorem tells you that this is A mod what's called the little violet. So there's a sort of isomorphism characterizing this categorical quotient. So in this case, there's a smooth map, so a smooth variety with a map, which I call pi tilde, over the regular locus of P mapping to this A. And so it sits in a Cartesian diagram. Like this. And I think that's all I really wanted to say about it. I was interested in this for a lot of different reasons, but my hope was to sort of view this as a generalization of the Grothendieck-Springer resolution. Turns out that in general doesn't exist if you try and extend this over the regular locus, but some things could be said. But the upshot for doing so, as was mentioned in the previous talk, was a theory of cameral covers in this setting. Namely, one's able to study the regular centralizer group scheme when we sort of move to this curve setting, and then you can develop a theory of cameral covers. So at this point, as I mentioned, my goal was to do this as sort of like the first few steps in order to try and tackle Ngo's work in this more general setting. But as it has become clear in a couple of talks, there are a couple problems that came up at this point. The first one is precisely this issue that was discussed in the last talk, namely that if I look at the regular locus over the stack, this is not a germ. And so this is problematic for trying to just see if the arguments run through. And I did not know what to do with this. And so thankfully, see last talk is now understood by the work of Thomas and Benedict. But another problem from the point of view that, again, my original motivation was the relative trace formula, was that once we get this, what is our goal? Like if our goal is to prove some form of a fundamental lemma, then we need a notion of endoscopic strata or mx to ax. So let me just say briefly what I mean. So the example, if we take the group case, so where G is 2 copies of H, and the involution is the swap map, then in this case, everything reduces to the classical setting. And so in that case, we have, let me write that down, and H to AH, this is the Hitchin fibration. And what Ngo studies is the supports of the irreducible constituents of this push forward. And in addition to the support theorem, he also characterizes, maybe I should say over the elliptic locus, characterizes strata in terms of the maps, where I have my Hitchin base for H, and there's a canonical map from the Hitchin base of some other group E, where this is my so-called elliptic endoscopic group. So the obvious problem is that even if even if one could solve the geometric question and seek to and prove the appropriate support theorem, you're not going to get a fundamental lemma if you don't have a notion of endoscopy. And so at this point, I kind of backed away and tried to return to the motivation and actually look for examples where endoscopy might come up from automorphic forms. And so let me say a few words about the relative trace formula. Periods. So I'm not assuming any familiarity with the notion of automorphic forms. All we need is that an automorphic form for G, if you'd like to think about it as it's a highly symmetric function, I'll say the real points of our group that satisfy strong invariance properties, say with some lattice inside of G, but we can think of it just as the integral points. So this is all we need to think about for an automorphic form here. And so we're interested in these things for lots of different reasons. They show up in many areas of mathematics. But for the context of the relative trace formula, what we're really interested in are things called period integrals. And so here comes the subgroup H from the other board. And so again, I have the notation X is G mod H. And so what is the period integral? So we are interested in I'll call it P sub H of phi, phi being my automorphic form. So morally, I have this inclusion of H, and so I can take my function, pull it back to H, and then try to integrate. And the invariance will line up so that I can say mod out by some the lattice in H. And so this is the sort of archetypical thing that you're interested in studying. And there are many questions that one can ask, but the most fundamental are, when are these zero? And if they are non-zero, what are their values? And so if this is not zero, then generally speaking, this is related to notions of Langlands functoriality. And if so, what are they actually equal to? This is in a great generality related to the special values of Langlands L functions. So this is the kind of thing that we're interested in studying. So the relative trace formula is a tool that we use to do this. Actually. So this works very similarly to what happens with the trace formula. Namely, what we do is we study these things in families. So what the relative trace formula does is it gives us a sum where we are summing over these various automorphic forms of these period integrals. And it turns out you end up maybe taking the absolute value squared, because that's what really matters in a lot of examples, plus some other things. And really there's some test function. This is like an identity of distributions, F, so there's some weight here. And by averaging over these, it turns out that what we get is a geometric sum, where I have these orbital integrals, so I'll call this O sub x f at x plus other terms, where in a very nice way, this is related to these quotients that we're seeing. So here, what I'm averaging over is these integral points of my symmetric variety, modulo the action of the H points. So this is in some sense like an integral point version of this quotient. Right. So this is sort of the object that we're interested in studying. You want to somehow, as with the usual trace formula, you want to study the geometric side, hope to maybe massage it into a notion of a stable trace formula if necessary, and then use that to extract information about the spectral side. And so what I did after I kind of got stuck here was to more or less just go looking for examples where there might be some stability conditions, some stability issues with these objects. And I kind of looked and talked to a couple experts in the area, and several of them told me that they didn't expect it to exist because, which is sort of based on experience, somehow the general notion of a relative trace formula is still being worked out. And a lot of the examples in the literature are, there's no issue with this, there's no stability issue like what I'm about to describe. But it turns out that it actually is important. And so let me just give the example that I found most interesting. So I'll take G to be, so now let's say K is Q, for example. And this will be a unitary group and rank 2n, and H will be UN across UN. So from my point of view, this is a very pretty example. It's related to the GL2n examples that Thomas mentioned before, but it's perfect from an arithmetic point of view because on the one hand, its periods are very important. They're very interesting. They're related. They're conjecturally related to central L values of standard L functions. So these are like the most basic objects for automorphic forms. And so it's a very rich example, but from my point of view, it's also very nice because the relative trace formula was not stable. And so this is sort of the example I honed in on and helped me kind of develop the thing that I'm about to describe. Please stop me at any point if there's questions.
Is not the kind of compact group we would
Say again?
Not the compact user.
No, yeah, this is not compact. I mean, it could be, right? In general, for this sort of thing, you always move to the quasi-split form. So this is really using the fact that I'm working over Q. This could be any unitary group that has an appropriate, like the permission space has an appropriate decomposition. Yeah. But certainly you could consider the compact case. All right. So what I want to say is just very briefly, I'm going to need to use some Galois cohomology in a bit. And so I wanted to say morally what I mean when I say we need to stabilize these things. So, orbital integrals. So for simplicity, I mean, this set is sort of over Z, but you do some massaging and you can reduce to sort of a local situation. So also when I'm working with a local field like QP or R or C, I'll let X be a point in the corresponding symmetric space over my field, and I'll assume that it's regular semi-simple in the usual sense. And so what this orbital integral is it's just a standard, I take some test function f on my variety, and I just integrate over the orbit for some choice of measure here. Doesn't matter. Where this is the stabilizer, h of x is the stabilizer. Okay, so these are the sort of objects which show up on the geometric side of the relative trace formula. And what is this stability issue? It's precisely the same sort of thing that happens in the context of the classical trace formula. Namely, if I were to take the orbit over the geometric orbit, so I take the schematic orbit over the algebraic closure and then look at its k points, that can decompose into finitely many rational orbits. And so in this case, so x and x prime are conjugate by h over the algebraic closure, but not by h of k. So the simplest example of this is if you take, let's say h acting as SL2 over R, and I let x of R be its the algebra. So this is not the same situation here, but it's something one might consider. And in this case, you can have orbits which are these two-sheeted hyperbola. If you take, I'm gonna have a hard time remembering an example. Maybe something like t minus t. The point is that there will be two rational orbits for SL2R because this is a connected group and there's two components to the set of elements here which have the same characteristic polynomial. And that's precisely what's being characterized here. This will describe a closed point in the categorical quotient, whereas these are the things that show up on the geometric side of the trace formula. So the point of stabilization is to rectify this difference. And in doing so, out pops these other groups, so-called endoscopic groups. Yeah, so just very quickly. So the point here is that these orbits, these different representatives are characterized by, so these xi are in bijection with a subgroup. It's a torsor for a subgroup of the Galois cohomology of this regular centralizer. And so this is sort of the thing that plays a role. And so the idea is to take this orbital integral over x and more or less just do a Fourier inversion formula over this finite group. That's what stabilization really is on this local level. So the stable thing, the thing which somehow is related to the point in the categorical quotient, is going to be the stable orbital integral, or sum over all these x primes, orbital integral at x prime. So this is the thing which the categorical quotient sees, and in doing so, you introduce these error factors, constant, non-trivial characters kappa on this cohomology group. And you just take this sort of an average, but you insert a character, and that's called that's the so-called kappa orbital integral. Okay. And so the point of the stabilization is this is what shows up in the trace formula. This is what the categorical quotient actually parameterizes as things associated to stable orbits like this. And the endoscopic terms are kind of what's left over that need to be interpreted. And so the reason I'm mentioning all of this is because I need to figure out precisely what the problem to be solved is in order to find the solution. And so with that, I want to go ahead and start defining. So the goal now is to define a endoscopic symmetric variety from the data of this character kappa.
This work, you don't have some kind of Picard stack that acts on your screens?
So it depends. If the regular stabilizers aren't abelian, then you'll have to deal with the non-abelian part of that. But in general, you'll have an appropriate action of torsos for whatever that stabilizer is. This is, I think, was. I mean, right now I'm going to just define the data, so I won't get to the actual action of.
No, just because these kappas are supposed to come also from some pi zero, or it's something different than this.
It's related to that, but only after the fact. What like I don't know. Somehow this is what comes out of the relative trace formula, and so the hope is that by combining what I'm going to say here with the work of Thomas and Benedict, we'll sort of be able to answer that question, or maybe they will. I'm not asserting anything. All right.
So let's go from here.
Kappa is a character on this homology, and it may be to the point that was just made, is that in general these regular centralizers need not be abelian. And so how does one rectify this? Well, there's some certain signs that come in from the harmonic analysis, but when you do that, you can replace the Galois cohomology with its abelianization. And so there's a well-defined theory of abelian cohomology, which will actually be the thing that shows up here.
Is that a finite abelian?
In this, yes, this will. So since I'm working over local field, this is a finite abelian. And you always have a well-defined map in this case. In many cases, this is a bijection. In the p-adic setting, it's always injective. Yeah, so there's ways. So there's a lot of sort of like subtle details about how to actually make this work that I'm kind of trying to gloss over. But given an orbit x representative x prime, you get an invariant in this non-abelian cohomology, and so you have to take the image in the abelianization. Okay. But for example, in the case that I mentioned, this case, everything's abelian, and so we already understand, as in the previous talk, what you should see as the fibers. Okay. So the endoscopic groups are defined on the dual side. And so we need to work on the dual side here as well. So I'll let G, H, and X be as before. And I'll also fix some other data that happily showed up in previous talks as well. I'm going to fix a maximal torus. So I have my involution theta. I'll fix a maximal torus A, which is maximally theta split, in the sense that it contains if you take the subgroup on which theta acts by inversion, it's the largest possible such torus. So we already have seen in some talks the dual notion associated to this data from Nadler. So Nadler associates.
So what you call a maximal theta split is a maximal theta split, or that's a maximal torus for G?
This is a maximal, I said, sorry, maximally theta split maximal torus. Thank you.
Which means that it's a theta stable maximal torus containing a maximal theta split torus.
Yep. So alternatively, you can fix a maximal theta split thing in any torus containing. Associates to this data a subgroup, which I'll call H sub theta. Really, I want to call it G sub theta as a subgroup of G check. And from my point of view, this is very close to what you need, but it's somehow we need a bit more. And so what what I'll need is the following. So I'll let B be any Borel containing my torus A. Then B acts, so this is a spherical variety, and so B acts with an open orbit. Yeah, I mean, I shall call X naught. And I'll let P of X be the parabolic containing Borel be the largest parabolic stabilizing this opening. So this is what's called the parabolic type. We saw it show up in some special cases in Brion's lecture this morning. It's the alternatively, it's the minimal theta split parabolic containing B. And why mention it? Because this is somehow this L of X controls the non-abelian nature of these regular centralizers. So for a general X, or I'll call it maybe Y in this open locus, regular semi-simple, we'll have a short exact sequence. Maybe I should just say there exists a regular semi-simple element in this open locus such that the short exact sequence, or L of X, acts via some torus quotient. And the kernel is precisely the stabilizer of my point Y. So this is some torus quotient by which this Levy subgroup acts on the symmetric variety, and this is precisely the regular stabilizer of this. All right. It's not necessarily abelian. For example, if G is GL2N, H is SP2N, then L of X is NGL2s. The quotient map is just take the determinant on all factors, and the regular stabilizer is the SL2s. So in general, this need not be abelian. Okay. So the point in mentioning this, so I just need to make one slight remark, is that A sits in here and also acts via this quotient. So we want to use an enhancement of Nadler's group due to Knopp and Chalky, but motivated by work of many people. Well, I'll simply quote Knopp and Chalky. I have this map of tori. So consider the dual map, AX check to AX, A check, the dual map on tori. So this sits as a maximal torus in G check. I'm going to lie a little bit. You have to sort of renormalize this in general, but for the most part, what they prove is that there exists a reductive subgroup GX check called the dual group and morphism, phi x, which is effectively unique up to conjugacy by this torus, such that this is a maximal torus in G check. And actually, what they do, and this is important for me, is they define a subgroup, Levy, of the dual group into which this maps such that the image GX check is the connected component of the fixed group of some involution on this Levy. So there's some involution here, which I'll call theta check, for which the image here is I take this Levy, this is the so-called associated group, I take its fixed points, and then I take the connected components. And so why this is useful for me, for our point of view, is that this allows us to define complex symmetric space which I'll call the dual symmetric space. Do I want to say anything else? Oh, I should say a few other things. I mentioned this group L, and I mentioned that it contains the sort of non-semi-simple part. That also is dual to a levy here. For those of you who have seen Binsby, Socrates, Venkatesh, this sort of controls the Arthur SL2. But a key point for us is that these two groups, the image of this dual group and this levy, effectively centralize each other. Centralized.
Can we see some examples of these two?
Yes, in the next board. Centralized.
Where is the nutmeg group in this diagram?
Great question. I'll say it in a second. Centralizes the image. All right, so some examples. I want to give some examples and also why do this instead of the Nadler group? Okay, for example. So let's do that one. So when X is this space of alternating matrices, then in this case, GX check is GLN, which matches the reduced root system here. And this maps into GLN cross GLN embedded inside GL2N in a block diagonal way, or depending on how I define things in sort of, the checkerboard pattern, if you will. And this LX check is a GL2 to the N sitting here in a way where this, you can think of this as G, and then these two will at least the derived subgroup of this will commute with this. So to Oscar's question, so let me make a few remarks. What's the symmetric space? This is the swap involution that fixes this, and so it's the double one. So you just get a cup. It's isomorphic to GLN. So in this case, X check is GLN, and it's actually like a twisted diagonal, but it's the same space. That's important for Langlands parameters, but not for geometry. So remarks. Where's the Nadler group? It's just the image. So phi of X is the Nadler group. This is somewhat obnoxious to actually verify, but you can do it just because of the language difference. I want to make two more remarks.
In the quasi-split situation, the levy is most of the time the group is always the group itself.
So right, with this levy or this
The levy,
this one.
the GX check.
Yes, so GX check with the associate, with the involution. In the quasi-split case, it's G check, except when you're looking at the GL 2n plus 1, GL n plus 1 cross GLN. That is the unique quasi-split case where this is going to be a GL2n cross GL1 sitting inside. Yeah.
So where to get Kappa gone?
Where is Kappa gone? Great question. That comes up. You guys are timing it perfectly. All right. So here's the key point, and I apologize for needing to use some number theory to define this, but I mentioned that this centralizer here effectively centralizes the Nadler group, the image of this morphism. What that will tell us is that this, when I dualize this sequence, the center of what I was calling that generic stabilizer over there will lie in this quotient. Where I'm thinking, this is the key point of it being a symmetric space, it embeds as a closed subvariety in just by the symmetrization. And so why is this related to Hugo's question? This is where kappa lives. So the reason being, by Tate Nakayama duality, this is isomorphic to the character group, the dual of this. Well, once I take the Galois action into account, take the Galois fixed points, and maybe the connected components. But so the point here is that starting with a character here, we're able to cook up elements in this symmetric space. So given a kappa, we obtain, maybe I'll call it kappa prime, an element of this complex dual symmetric space. And this process, you may be concerned, this will end up giving a unique G check X orbit, a Galois stable GX check orbit on that symmetric space. And so that's sort of the key observation. How much time do I have? Not enough. All right, so I've said some things about Galois, and I want to work over a general field because that's where relative trace formulas live. And so the third comment is that we need to take the gamma action into account. So more or less everything in that diagram has an appropriate Galois action that corresponds to the Galois action on the dual group that gives you the Langlands dual, the L group. For those of you who are familiar with this, it's not unique, but it's more or less like the non-uniqueness is important because it more or less tells us like maybe I want periods where I twist by a character or something like this. And so that's all that matters. But I need that in order to actually get this statement of the duality situation. Okay, so I'll just make the following quick proposition. With this information, namely these diagrams and the Galois action, I need one more piece of information. So there exists a symplectic GX check semi-direct Galois representation called SX, such that the data of this map going into G check in this representation, all with the Galois action appropriately situated, determines this symmetric variety up to inner twist. This is a purely, this is a meaningless statement in the geometric setting, but for the point of view of endoscopy, this is really crucial for me to actually define the endoscopic symmetric space. I'm going to get some data on the dual side, and I need to tell you that up to something that's not relevant for the trace formula, there's a unique thing on the other side inducing it, and that's what this tells you. Okay, so let me just give one. What time did I start? Oh no. Okay. Let me just give a quick example as to why we need all of this, because you may be not convinced. Maybe Nadler was enough. So example, I'll take the following two very simple symmetric varieties with very different arithmetic properties. So let K be R. X will be SL2 mod split torus, so just the diagonal torus. And X prime will be SL2 mod S1. In this case, the Nadler group is just the whole PGL2. This is G. Whereas this setup, both spaces induce SL2 mapping to PGL2 via the quotient. So this morphism need not be injective. But they both induce the exact same data, just on the even taking Galois into account. It's only when you take the symplectic representation with its Galois action into account that you can separate these spaces. So in this case, SX as SL2 reps, they're both just the standard representation, but Galois acts by a sign for the non-split torus, or X prime, but it acts trivially for the other variety. So we really do need this additional. I mean, you see everything kind of happening here. The symplectic representation doesn't make sense on SL2, PGL2. You have to pull back to the double cover, and the Galois action distinguishes.
Is this SX related to, in many cases, densely separated vectors have a representation of the dual group? Is this related to the SX here?
Yeah, so more or less, I kind of stumbled upon some of their things without knowing it. Yeah, so this will be effectively what's happening here is there's a graded representation conjectured, and in the first graded piece, the part that's associated to central L values, you're supposed to get something symplectic. And what's happening here is sometimes Galois stabilizes the obvious Lagrangian, and other times it doesn't. So you have to switch Lagrangians to get something Galois stable, and that's what's happening here. So this is all compatible with Binsby-Sugger's thing. All right, what's the upshot of all of this? Let's recall so I have a regular semi-simple point in my variety. Now K, here's some local field. Everything here was, K was relatively arbitrary. So now I'll just take K local. And let kappa be a character of the abelianized cohomology of the regular centralizer. And things get a little hairy when this is not connected. So that's, I'll impose that assumption right now. Assume H of Y is connected. Which again works just fine in this case, but also in all these unitary cases. So by what we just discussed, on the dual side, to obtain a point that's unique up to a certain action in this dual symmetric variety. So I have a diagram of this form. I have a point, a semi-simple point here. And so now we use the fact that this is a symmetric space. There's a well-defined theory of descent. At any semi-simple point, I can take the sort of local model of the representation of the space there. And so what I get via this descent notion is a stabilizer in this group here, and a stabilizer in GX. I mean, here, this is literally just the stabilizer of this semi-simple point under the action of GX check. And I'll do an example of this in a second. But the point here is that I get a smaller group associated to this semi-simple point. And actually, since this will be a semi-simple point in the larger group GLN, or sorry, G check, I actually see all of this inside just the centralizer of this. So the theorem, let G kappa be the quasi-split endoscopic group So this is a centralizer of a semi-simple element in my dual group. So this is precisely dual to an endoscopic group. It may no longer be elliptic. There may not be an elliptic something, but it's some endoscopic group. So let's consider the dual. This is the endoscopic group for G. Then there exists a unique up to inner twist symmetric space. Decorate everything with kappas. Dual to these groups, these stabilizer groups that we just saw. And such that if I take the symplectic representation associated to this endoscopic variety, and there is a morphism to the restriction to this smaller stabilizer, and this is an isomorphism. I think that's all I wanted to say in that. All right, so that. So this is what I'm saying is the definition I'm giving for an endoscopic symmetric variety. Okay, why? Where does this connect to what we were discussing earlier? There's more or less an immediate proposition from this is that for X and H and X kappa, H kappa, as above, we obtain canonical maps. There exist canonical maps of the categorical quotient of the endoscopic variety to the categorical quotient of X. And if G is the Lie algebra of G and you have the corresponding grading so that P is sort of the tangent space at an identity for these varieties. And I similarly have G kappa, H kappa, P. Then we similarly get phi, Lie. Maps on the categorical quotients there. And so this is the point here is that this sort of solves that question that we started with because I've done everything for the actual symmetric space, but everything passes to the Lie algebra just fine. And so now if I take, say I'm working in a function field setting, I can take the mapping stack to the various quotients and get so let's say C is my projective curve. Then we get a map from AX kappa, the relative Hitchin base to AX. And so the point is we can use these maps to sort of resolve that question that we started with. Okay, so I only have a few minutes left, and I would like to maybe just give a few examples. And I don't think I have time to state the applications that have already been worked out. But in many cases, this has been checked on the in the harmonic analytic setting. So one of the things that I was able to do when developing this in special cases was from, I guess, 2019, I think, for K, say, p-adic, and X is this unitary case here. The possible endoscopic varieties are U2A cross UA cross UA, U2B cross UB plus UB, where A plus B is equal to N. And in this situation, I proved the fundamental lemma here. The fundamental lemma holds. Which is a rather long-winded proof using a lot of harmonic analytic tools. It by no means reduces to previous cases of the fundamental lemma. This is so I expect, like, if this is only for characteristic, I said K was QP, but in general it works in characteristic 0. So the characteristic P case is still open, but surely will can be resolved. I hope. So let me, maybe in the last minute, just give a table of examples that kind of generalize this. So if I were to take the sort of non-quasi-split version of this, where I would have something like U 2n plus R, UN cross UN plus R. One thing which I don't think is maybe as obvious the way that I presented things, but the degree to which these are non-quasi-split is constant. So here you have this. This corresponds to a non-quasi-split group. So will this. It will be something of the form U2A. You'll have a quasi-split part, non-quasi-split part, where A and B add to N.
R is bigger than 1.
R here is greater than or equal to 0. So just including the case that I just.
So at least in the usual sense, the UN n plus 1 is quasi-split.
Yeah, UN. So, but this is still true. Yeah. This is sort of also keeping track of the non-temperedness of these varieties, which is somehow almost equivalent to being quasi-split, except in that one case. That's related to your prior question. So this thing should distinguish no cusp forms, or unless they're endoscopic, and same thing here. Maybe some fun examples in the last minute is if you take SO 2n, so another quasi-split case. So n minus 1, SO n plus 1. This corresponds to the other quasi-split, non-split, even symmetric group in the real setting. Then you'll get sort of the trivial part. So SO2, but it's completely fixed by your involution. And then SO even minus 2. So and finally, my favorite little case, if I take SP, so a non-quasi-split case, SP4n, SP2n squared, we get SO4n GL2. So I don't know. I just wanted to give you some examples where this this works, and I think I'm out of time. So there are several other cases where, on the harmonic analytic side, this has been verified that the conjectures sort of corresponds to stabilizations of trace formulas. I have a student working out some low rank cases now, but maybe I'll stop here.
Any questions?
I have a question. So this approach where you, instead of taking another group, you have another symmetric variety, allows for a question that I don't know if has anything interesting. If you play now the same game to that variety, do you get anything interesting?
Yeah, so this is a good question. So in general, I mean, there's this, the question was asked, which kind of brought up the notion of the relative Langlands duality of Bensby Sacklers and Hitchin. When we get very constrained symmetric spaces, these X checks, they're always going to be something called minimal in the sense, so morally speaking, you'll get things where you take a maximally split torus, it decomposes as a plus part and a minus part, and you'll need these two to have the same rank. That's a very strong constraint on symmetric spaces. And so what's kind of hiding in this, like needing to join this vector space in this other group, is that there's actually a more complicated G-check Hamiltonian variety, which is in correct sense dual to these symmetric spaces. So it's very rare that you'll actually get just two symmetric spaces dual to each other. So, but if you on the dual side are willing to work with, instead of maybe just a symmetric space, you take something like X check, and then you do some parabolic induction up to G check, and then this is no longer a symmetric space, but it's a nice spherical variety, then this will be appropriately dual to these sorts of things. They somehow fit in a larger family. Yeah.
When you mentioned that there is this map from AXK to AX,
Yeah.
What do you actually mean? That there is a summand of the decomposition theorem, or
I'm simply defining, right, so my motivation was to simply give the correct, or a map, so that like when the appropriate geometers come and prove the correct version of the decomposition theorem, you'll get these strata and you'll be able to associate them to endoscopic varieties so that it makes sense to see if we can prove the fundamental one. Because otherwise you're just going to prove it, something about the strata, but you can't necessarily relate it to the stable part of another symmetric space. So that's what this is trying to resolve. It also gives a lot of examples where the sort of behavior that, well, okay, so I'll just say random things, but there's a lot of things you can say about specific varieties where in particular you'll expect full support in general, but at least over the anisotropic, the elliptic locus. Yes.
So you had this construction of the dual symmetric variety.
Yes.
And then you had this levy in the Langlands.
Yes.
So is that levy always the fixed point of an involution there?
I've thought about this. Like if
It's like many of them.
in many cases it seems to be, but I'm trying to think of the example where I couldn't see it work. Because not that many levies. So for example, well, what is no, I think even just that case. If you have GLN mapping to GLN squared. So this is a maximal levy here. But the levy LX was, oh, you meant this levy.
This works.
It does work here, yes. I don't have a good counter.
So 2 times SO2 and minus 1.
Yes, well, the reason here being that all of these are examples where the endoscopic, this kappa that you use to take fixed points on the dual side, all has order 2. So these are all inner, these are dual to inner symmetric subgroups of the dual group. But I haven't checked, for example, like exceptional cases where you might get things of higher order. So that's a very nice question. I don't know the answer.
So I mean, I have 2 related questions. One, assuming that you have full fundamental lemma and transfer conjectures, then could you do the whole stabilization?
Yeah, so this is sort of work in progress. That the answer is yes, at least under this constraint that I gave. I've erased it since. If I assume the stabilizers are generically connected, then things more or less work. But there's a lot of cases where that's not true. And there's also reasons from harmonic analysis to expect that just has different behavior. So I don't know.
There's a second question is, assuming on that rule, that should imply some identity on the spectral. So
Oh, yes. So
is there anything known about equality of periods in different groups?
yes. So the simplest example where in hindsight, this is precisely what's happening, is you take one example here that I've not mentioned because it only makes sense over a is Galois periods. So where you take some quadratic extension and then some representation over, say, C, and then you integrate over the real group. This is a very interesting and rich case to consider. And the first case that was studied was GLN, let's say L over K is degree 2. So I'll have a GLN over 2 modulo some unitary group defined over K. Then in this case, the only sort of endoscopic automorphic forms in the stabilization will be Eisenstein series, because you're going to be looking for base changes of endoscopic lifts from the unitary group. And in that case, what you get is that the appropriately normalized period over the unitary group of this Eisenstein series, some normalization, is a finite sum indexed by some base change map of an L value and some Euler product. And so in general, these will be fibers over various punctorial maps. You'll get these there's a couple other low rank examples where you get that in the context of an endoscopic period, you're going to not get, even if it's generically Eulerian, you're going to get sums of Eulerian factors. And there's local questions as well.
Okay, so no more questions. Thanks, Spencer, again.